Alright, in this video we're going to look over the answer key for Monday, March 30th. And our topic today are glycoproteins. We've talked about glycogen, sugars, we've talked about proteins, and now let's talk about combining the two. So that's what our lecture went over today. And specifically, we're going to look at proteoglycans, which are these huge sugar protein complexes that are usually on the outside of your cell. Hyaluronate being one good example. If you were in class, you would see me jump up and down, showing off that my knees has a bunch of hyaluronate in it. That's why my knees aren't exploding. Unfortunately, in video format, I can't show that. But let's get into the questions. So, following the synthesis, oh, it looks like I saw a B there. I meant to delete that, but that's alright. So, following their synthesis, many proteoglycans are stored in highly condensed state in intracellular compartments. These compartments also have calcium, which are pumped out as proteoglycans are released extracellularly. What are these calcium ions doing? Alright, so proteoglycans, the sugars on these are highly charged, highly negative. These are the sulfur sugars that we talked about. And so naturally, they would want to repel each other. Negative charges repel. But if we want to condense them, if we're not ready for their deployment, we have to make the negative charges come together. So we put a calcium 2 plus ion to go and interact with all the negative charges. You can move negative charges close to each other as long as you have a positive charge sandwiched between them. And so this is a way to condense our proteoglycan. Then when we're ready for deployment, we can release it and the negative charges will naturally repel each other, which is what we want. That's what hyaluronate is doing. It's making a gel, so we do want it to be fully extended, so that's why we don't need the calcium anymore when we're ready to use it. B is a repeat, but fiberglass growth factors bind to glycoaminoglycans. So what amino acid? Glycoaminoglycans are negative, so they probably have positive lysine and arginine. Alright, so when performing SES page, glycoproteins are likely to come out as a smear, while proteins that don't have sugars come out as a band. Please explain this. Well, in the lecture video, I talked about how these glycoproteins have microheterogeneity. That means that when you add sugar onto proteins, it's not really exact. What I mean by that is that take any protein you want in the human body. Your body is going to make it the same exact way every single time, same number of amino acids. When we add a sugar onto a protein, we don't add the sugar the same every single time. My example is a protein X is glycosylated. One molecule could have 4 glucoses and another molecule of X could have 3. Your body's just kind of random that way. That means each glycosylated protein has a slightly different molecular weight. And SES page is separated by molecular weight. So you get this smear because this is all one protein, but they're just have different numbers of sugars on them. So you're getting a smear because they're slightly different weights. Right, so the other topic for today were bacterial cell walls, in which that has a peptidoglycan layer around it. And the peptidoglycan layer is protein plus glycan called peptidoglycan. They have some very interesting features that we went over in the lecture video. So some questions you might see related to that. Which is not a structural component of the peptidoglycan? Well, it's sulfate, but let's talk about why the other ones are true. So disaccharide, yes. Every peptidoglycan has a disaccharide, N-acetylglucosamine and N-acetylmyrmic acid. Acetyl group, yeah, it's in the name. Acetylglucosamine, acetylmyrmic acid, tetrapeptide. So it doesn't always have to be a tetrapeptide. Sometimes it's a pentapeptide. Sometimes it's a tripeptide. But you always have a amino acid connected to your peptidoglycan. So which feature of the peptidoglycan is not essential for structural stability? And acetylmyrmic acid? Nope, it's right there. D amino acids? So we have D amino acids in the peptidoglycan layer. We'll talk about why that's important in a minute, but this is one of the few places in nature on Earth, we found D amino acids. 99.99% of the time, they're going to be L. Peptidoglycan is your exception there. L amino acids. Well, we still have L amino acids in here. It's just one D alanine. D monosaccharides. So when we went over the monosaccharides, we did not go over D monosaccharides because we don't use those in biochemistry, so they are not found. Okay, so peptidoglycan layer, the way you can think about this is a net with a lot of holes in it. So why do we have holes in the peptidoglycan layer? Well, so nutrients can go through. This is on the outside of the cell, but we still need food to go into the cell. We need oxygen to go into the cell if you're an oxygen-using organism. So if you don't have holes, you can't get nutrients through. You can't export waste out. Now, why does peptidoglycan have D amino acids? All right, so if everything uses L amino acids, and this peptidoglycan is your armor, more or less, it's your outside shell, it makes sense that you want to have your armor have a trick with it. By that I mean the proteins that your enemies could use to kill you are going to be looking for L amino acids. Well, if you throw a D in there, you're going to stop enzymes like lysozyme. You're going to stop getting cut because your enemy's enzymes shouldn't recognize a D. So it's that evolutionary thought. It's for protection, so you don't get hydrolyzed, you don't cut that peptide bond. Now, there are enzymes that can cut that D amino acid, but bacteria do make D amino acids, and that is the reason for that. And that is it for this video, and I will see you in the next one.